What's up, people? Welcome to Atomic Structure, and let's move on with atomic structure. And today we'll get into the real thing here. And the real thing about here is the evidence for the quantized electronic energy levels discussed using atomic spectra. Now, in the last science education video, I discussed about the history of the electromagnetic spectrum, that is a continuous spectrum of the various frequencies that is in the electromagnetic radiation. To discuss about that thing, we'll move into two types of spectrum that we have, and these two types of spectrum are called, one of them is called the continuous spectrum, that is the electromagnetic spectrum, and the second one is a discontinuous spectrum, and more importantly known as the line spectra. Now it is important to understand that if you search spectrum on Google, if I do the same thing right now, if I search spectrum on Google, then spectrum, according to the dictionary, means that is a condition that is not limited to a specific set of values but can vary without steps across a continuum. Right, but it is important to understand that spectrum actually means a piece of, let's say, impression of what electromagnetic radiation will give us. So this spectra does not equally imply that it has to be a continuous spectra, but it can also be a spectra with lines, because it may hit at certain points where it glows and thus give us a line spectra. So that is what the line spectra means in a discontinuous spectra. Okay, now if we talk about the continuous spectrum, we know that the continuous spectrum is one which includes the electromagnetic spectrum, in which if the frequency is ending at around, say, 9 into 10 raised by 14 hertz, then there is another electromagnetic radiation which have a frequency of 9.00000 till some infinite number, let's say 9 plus into 10 raised by 14 hertz. So the spectrum white light that we can see ranges from violet at 7.5 into 10 raised by 14 hertz to red at 4 into 10 raised by 14 hertz. Such spectrum is called a continuous spectrum. The continuous because the violet merges into blue, the blue into green, and so on. Right. This is the spectra that we normally see in a rainbow. Right. So we have different colors, and if you see that all these colors merge themselves, so this is a continuous spectra. Right. So what is happening here is that when if white light is coming to us, the white light consists of all these colors and they are merging into one another. But if in this case what we do is, like, if we have light with us, and the light is moving in this direction, okay, so this is the light we have, and what I do is I put an atom in front of it. Then this light will just give all its energy. Like, this light has some energy of h mu, then it will give all its energy into this atom here. The electrons will gain those energy, move into certain higher energy level, and this higher energy, and when those electrons come back from the more stable lower energy state, it releases some kind of electromagnetic radiation. And when this electromagnetic radiation is seen, well, we know that this electromagnetic radiation is not continuous. Okay, so what is happening here is, if we consider, let's suppose that I have an atom like this. I have an atom like this. So there is one atom here like this. Okay, let me draw it in the middle so we can understand it better. And okay, so similar, we have another shell like this. Yeah. Okay, let me just draw it in the middle so that it's okay. It's an approximate equal type shell. You can see that. Okay, so we have an atom like this having a shell like this. So I draw another shell. Okay, so we have three shells like that, and what we have here is the nucleus in between. So we have this like this, the nucleus that we have, like positively charged, the rest are neutrons, right? And the rest electrons that we have it in the orbit. So there is an electron here, the electron, and another electron here, and another electron here. And let's suppose that we don't know about the electronic configuration, and we are just discussing about the normal electron energy states. So what is happening here is that according to the Rutherford model of atom, this should have happened. Now, Rutherford also gave us another small theory. He said that the lower energy state, or this energy state here, if I draw this energy state here, if this one is a lower energy state as compared to this energy state, right? So that is very much implicable, because if we consider the potential energy, right? If we consider the distance from here and this distance, then we can easily say that using the potential energy formula, that is that is minus of k q1 into q2 over the distance d. So if the distance increases, and distance decreases, right? This whole thing decreases, and if this whole thing decreases, then the potential value increases. Okay, so it is a high energy level and electron is a lower energy level, and another any kind of substance in this world, according to a thermodynamic concept, has to live within lower energy state. So even if it is an electron is a part of a matter, then it has to live in this low energy state. And that is what is happening here. The electron wants to live in low energy state, but when certain kinds of electromagnetic radiation come from outside, let's suppose that this electromagnetic radiation is coming, then it will move and hit the electron. So the electron will gain this energy here and will move to this position here on the next energy state. But because it is seen that, okay, let's first discuss that what will happen after that. Now this electron is at higher energy level state, but it won't live in this higher energy state. It has to come back to the lower energy state, and so it will come back to this own level. In this, it will lose some energy, and this energy will be lost in the form of electromagnetic radiation. So a new type of radiation will come out from this one. Similarly, a different type of radiation will come out in case it had gone transferred here and would come back, and therefore it would have another type of radiation. Now, similarly, if we draw this radiation, if we draw this type of radiation onto a paper plate or a fluorescent kind of a sheet, then this radiation gives us certain kind of lines like this, right? So these kind of lines is called the line spectrum, and it is called the emission spectrum, because this is the spectra when an atom emits the electromagnetic radiation. Therefore, it is called, let's write it. It is called the emission spectra. The emission spectra. And emission spectra is more important for us than the other type of spectra that happens in line spectra, and is called the absorption spectra. Okay. So this is called the emission spectra, or another part which is called the absorption spectra. And the study of this emission absorption spectra is referred to as the spectroscopy. Okay. Now, we have discussed about the line emission spectra and how does it happen. Now, what are the consequences of the result of this line emission spectra? Well, the line emission spectra is more important is of the hydrogen atom, because it is more easily seen that in the hydrogen atom the electrons will move above. Now what is happening here is that when Rutherford developed his model of atom, he said that there is a certain lower energy level and a higher energy level, and according to classical physics, this lower energy level, let's say Le, and this higher energy level He had to be continuous. So if this is moving here in this direction, then it has to be continuous. That was a case decided by Rutherford model of atom. But what happening here was that he did not go into the experimental research. When a scientist named Balmer in 1885 went to the experimental observations, he moved into the spectral line series. Now we know that the spectral lines are actually, in physical observance, are electromagnetic radiation, which might have some kind of frequency, might have some kind of wavelength, and we also know about some kind of wave number. So Balmer in 1885, on the basis of experimental observations, that if spectral lines are expressed in terms of the wave number, then the visible lines of the hydrogen atom spectra was look something like this. So the formula was given as 109 into 677 upon 1 upon 2 square minus 1 upon n square, and this is centimeter inverse. Now n, here to be noted, is an integer. So that means that these spectral lines have certain discrete values. Now, if this spectral line has certain discrete values, it means that the energy difference also has some certain discrete values. But how can you find out that? How can you prove that it has to have certain discrete values? To know that it has certain discrete values, we know that the energy of any photon or any electromagnetic radiation is hc by lambda, and h1 by lambda is the wave number, so it is hc into the mu number, or the mu bar, or the wave number. Now this is equal to hc times 109 into 677 1 upon 2 square minus 1 upon n square. Now this is the energy difference. Let us say it is delta E. Delta means the change in the energy, and this is the energy difference between the two shells here. Right. So if we have two shells in this part, then if you move in this direction, then this energy difference is the delta E that we are talking about. And if n has integral values, the n belongs to integers, then the energy difference has certain values. Thus, at the end, it has to be described that these energy levels are quantized, that certain energy levels can only exist. It is not possible, it is not at all possible for a continuous system energy to happen because of the spectral line series that we have for hydrogen atom. Now it is also supposed by Rutherford that this spectral line, that the hydrogen atom has only one shell because of one electron revolving, but this one electron can also go into higher energy states, means there are infinite number of energy states above that, but they are not continuous, but they are defined by a principal quantum number called n, which is the topic for the next lecture.